Hello everyone. In today's video demonstration, we'll be diving into the world of I2C communication, a powerful protocol used to connect microcontrollers and peripherals. We'll be using HT66F2030 MCU to demonstrate how I2C works both as a master and a slave. By the end of the video, you will understand what I2C is and how it works, how to write I2C master and slave code, how to test I2C communication in a real world scenario. Before we jump into the code, let's quickly understand what is I2C. I2C stands for Inter-Integrated Circuit. It's a two-wire communication protocol that uses SDA, serial data line, for transmitting and receiving data, SCL, serial clocks line, for synchronizing communication. I2C is widely used because it's simple, requires only two wires, and supports multiple devices on the same bus. Each device has a unique address, and the master can communicate with any slave by specifying its address. In today's demo, we'll be using HT66F2030 MCU as both master as well as slave to show how it works in practice. Let's take a look at the code. We'll start with I2C master code. The master code is responsible for sending a start condition to initiate communication, sending the slave address and data, waiting for an acknowledgement from the slave. Coming to the key part of the code, function write byte. Function I2C start sends start condition. Coming to the key section of the code, function I2C write byte, we pass the arguments such as slave address as well as data. Function I2C start sends the start condition. Function I2C write byte slave address sends the slave address and waits for the acknowledgement in the next step in I2C wait acknowledgement. Function I2C write byte data sends the data from the master to the slave device, and again it waits for an acknowledgement from the slave. At the end, function I2C stop sends the stop condition. In the main function, we are clearing the GCC watchdog timer and initializing SCK and STA pins as GPIOs. Since in our Altec microcontrollers, we have to make use of the bit banging method to transmit or receive data when used in master mode. In the while condition, I am transferring a write byte passing the slave address and data 0x05. This was about the master code. Now let us dive into slave code. Coming to the slave part of the code, the slave code listens for its address on the I2C bus, receives data from the master and sends an acknowledgement. It sends data back to the master when requested. The I2C slave address is 0xA0 for the slave. Coming to the main part of the code, which is written inside the interrupt. First, we'll check the address match interrupt. Inside the if condition, we check for the SRW bit to check whether the slave is in transmit mode or in receive mode. In transmit mode, the HTX bit has been set to 1, which sets the slave to transmit mode and sends a data to the master, in this case which is nothing but 0x55. In the else condition, the slave is in receive mode, master wants to write, the HTX bit has been set to 0, which sets the slave to receive mode and sends an acknowledgement after receiving the data. In the data interrupt, the if condition checks if the slave is in transmit mode, which means master is reading. If RxAK bit has been set, master stops receiving, no acknowledgement received, and the HTX bit has been set to 0, which switches to receive mode, sends acknowledgement and clears the data register. In the else condition, master wants to receive the next byte. In this case, it is 0xAA, which successfully sends the next byte to the master. In the else condition, the slave is in receive mode, master is writing in this case. The I2C read data variable reads data from the master, sets flag to indicate data received, and sends an acknowledgement back to the master. This code ensures that the slave acknowledges the master and the processed data correctly. Now let us load the code into the microcontroller using the ICP option available in our IDE. Once the microcontroller is connected to the IDE via the E-Link, we'll click on the ICP option, start programming by setting the voltage to 5. As you can see, download is OK and IC is locked. We'll quit the process. The slave code has been successfully dumped into the microcontroller. Code is running. We have opened the logic analyzer window. Now let us configure I2C in this logic analyzer. We'll click on Analyzer, click on the I2C option, set the SDA and SCL line. In my case, I have connected SDA to channel 0 and SCL to channel 1, and we'll save these options and run the code. As you can see, now let us see the I2C data in the logic analyzer. The master sends the bytes 0x05 to the slave at address 0xA0. As you can see, the master has sent address 0xA0 and received acknowledgement, after which it has sent the data 0x05, for which it also has received acknowledgement. In the logic analyzer, you can see the start bit, the slave address, and the data with acknowledgement. Coming to the read function, as you can see, we have successfully read from the slave 0x55 and 0xAA are the data which has been sent from the slave device to the master while reading it in the master MCU. You can see the start condition, the slave address, and the slave data. Now let us set up the hardware. First we'll connect the SDA and SCL pins of the master and slave devices. Add a pull-up resistor of 4.7 kilo-ohm to both SDA and SCL lines. Connect the ground of both devices to ensure a common reference. The master lines SDA has been connected to PA7 and SCL has been connected to PA6. The slave device SDA is PA5 and SCL is PA1. I have also connected a logic analyzer to monitor the I2C signal. This will help us verify the communication. We have successfully demonstrated I2C communication using the HT66F2030 MCU. You have learned how I2C works, how to write master and slave code, how to test and debug I2C communication. Thank you. If you found this video helpful, stay tuned for more such videos.